their ability to impart an elasticity to an interface. And this is something, so it's called Marangoni elasticity. There's also a different flavor according to the type of surfactant. So basically, according to how quickly you have a soap film, it can have Marangoni elasticity, which is basically this elasticity, which we see is resistance to surface divergence. And there's also the possibility of, if you have soluble surfactants, that they can diffuse onto the bulk and you get another type of elasticity. But the most common type of elasticities is Marangoni elasticity. And this came up first in studies of bubble motion. So when bubbles are small, they move at a speed which you would anticipate if they had a rigid surface rather than a free surface. And this is because the surfactants, which again like to be on the molecule, whenever you have whenever you have basically any fluid, unless it's super clean, will have some surfactants in it, and they will migrate towards the surface. They migrate towards the surface, and so as the drop rises in this direction, the streamlines around the bubble will sweep the surfactants backwards, and so that you then get a gradient. And this gradient in surfactant concentration gives rise to a surface stress, which rigidifies the surface. So basically, this then, you have a rigid cap on the bubble, and so its rise speed is different. And this is, you got around this by making this, if you put in enough surfactant, then you get surfactant everywhere, and you no longer have gradients in Marangoni stresses. So you can avoid this by having either very clean water or very dirty water. Okay, and so these also, again, if you just think of the surfactants imparting an elasticity to the surface, then you realize that any surface, any motion, fluid motion which has non-zero surface divergence will be resisted by surfactants, and that's the case with waves. So we know that we're creating surface when we're deforming an interface from a plane, but if you have wind, then this will naturally arise. The point is, the waves also have non-zero surface divergence. Okay, so basically, imagine if this surface area is being increased here, then you're decreasing the local surfactant concentration, and so increasing the surface tension relative to there, and so you basically get these Marangoni stresses which drive small-scale motion. Okay, so if you have wind blowing over water, we'll solve this problem. But when you have wind blowing over water, the most unstable wavelength has the wavelength of the capillary length. So it's on the order of a few millimeters, and so there you get this huge dissipation on this scale, on the millimetric scale. So those waves basically get damped by the presence of surfactants, and so you'll tend to then push the most unstable wavelength upwards. Okay, and so this is something that you'll see when you see the wakes of ships. You see there's always a sort of a glassy region, and this is because of the surfactants which they either stir up or they emit. So if they're releasing chemicals onto the surface. So again, we mentioned Benjamin Franklin. He noticed the Bermudan spear fishermen would throw oil onto the surface of water, and this would all play the same role in killing the surface waves, thus allowing them to see the fish they were aiming for. And this came up in satellite imaging, satellite tracking of submarines. So they noticed that they basically had a new satellite system which could get the topography of the surface of the sea down to millimetric scale. So you actually resolved capillary length. So you could basically see where there were and where there weren't capillary waves. And they saw that there are basically capillary waves everywhere except in a few stripes. And they noticed that these stripes were actually the wakes of submarines. So the submarines basically, as they go along, they generate a vortex, and the vortex sweeps up to the surface. And basically, if you have a vortex hitting the surface, it'll sweep up biomaterial, and so this biomaterial will act as a surfactant, so kill the waves in the wake of a submarine. And so this is, of course, even when they're at depth, so it's a pretty bad thing if you're trying to go around surreptitiously. So the Navy has invested some money in this problem. And this is also apparent when you, this is a picture which I took off the back of a whale watching boat in Boston. I kind of like this picture because it actually looks like a footprint, but it's several meters long. But basically as the whale dives, it generates a pair of vortices, and the fishermen, or the whalers, would use this. They call these the footprints of whales, so they'd look for them. They look for flat spots on the surface of the ocean. Here, the ocean was relatively flat, but I've been out on days where there were big, swells, several meters, and nevertheless you get these very glassy regions with no capillary waves on them because of this effect. So again, it's the sweeping up of biomaterial and associated suppression of the capillary waves, okay, through this Marangoni elasticity. Okay, so I was going to end. So here's another one. If you have wind blowing over a puddle, then you have capillary wave. You expect to have capillary waves everywhere. So if the wind is blowing strong enough, again, the most unstable wavelength the most unstable waves are capillary waves. But you have this region here where all the surfactant accumulates, and so there the waves are killed by the same effect. And so as the wind will blow, you have this flat region here, then waves elsewhere, but then the wind will die down, and you'll see this front move back, and the waves die, and then so you'll start off, and there will be waves everywhere, and then again the surfactant. So you sort of see this front moving back and forth. Okay, so now we get a murder mystery. Okay, so here's the murder mystery. This was published about 2 centuries ago in Nature. So I'll give you the story. So this is in the Caribbean. Somebody's a person went missing, and it was the wife of a fisherman. No one knew where she had gone, and they would look for a couple of days, and it was a mystery what had happened. And then they were all sort of hanging out in their local bar, looking out over the water at night, and they saw that there were basically waves everywhere except in this one patch. This is in the Caribbean. They're known to be sort of like what do they call this? Like piranhas, fish that would eat flesh. So what's happened here? Who killed the woman? That's the question. Who done it? Who done it? Yeah. Give up?
That's things from her body there.
There's her husband. How did you know that?
Well, that's the only character you mentioned, right?
Yeah, right. That's right. In Nature, 1880. Okay, so it's 130 years old. But so their husband, a clever young fellow of about 30, had taken her body and thrown it in, and figured that the body would be eaten by the fish, and correctly so. But he didn't realize that you would get a surface signature. This is very good, very good writing. Would set free the matter which was to write the traces of his crime on the surface of the water. Yeah, basically, yeah. Again, sort of biomaterial is always surface active. So that was that's the murder mystery. So the husband was found guilty and executed. Fair enough. Okay, so that's the end of the surfactant story. So again, you should sort of have a good feel by now for surface tension. Its role is basically to generate curvature pressure, so try and keep interfaces flat or spherical if they're very small, but basically to minimize the surface area. And then you have the second effect. When you have contaminated surfaces with surfactant, then there's an additional role, which is to there's this effect of elasticity at the interface. Okay, so the next couple lectures we're going to look at jets, fluid jets and sheets. So these are basically when you look at the fracture of a fluid volume. So we start with a bucket of water. Well, eventually, we know that if we throw it out of the top of a building, you're going to eventually get drops, and we want to try and understand how this happens, and also consider other geometries, so the dynamics of jets and sheets. So here's a nice motivating one, motivating video. So here they actually put paint on a vibrating speaker, and so you generate all these instabilities. So a lot of these we'll be looking at. So the pinch off of fluid threads, the breakup of sheets, such as you see here.
Yeah, but this paint is like what, floating on water or something?
No, it's just sitting on, it's basically being excited by the vibration, so being thrown upwards. It's in air.
But since there are several colors, it's probably floating on water, right?
No, it's just basically put a bunch of paint on a loudspeaker and levitate it. It's an ad. Okay, so, all right, so let's, the first problem, we're going to look at the instability of jets today, but we'll first look at a simpler problem, which is simply what happens when you turn your tap on. We know that the fluid thins, so can we predict the size, the shape, and the speed as a function of distance from the from the source? And this is sort of basically a Bernoulli problem. So then we're going to look at the pinch-off, and this is a canonical problem. So basically the pinch-off of a fluid cylinder into droplets. Okay? So if we look, so we have some nozzle of radius A. We sort of get the understand that the thing's going to thin as it gets down because it's going to accelerate, and the flux across any given layer is going to be the same. And we have surface tension, which is also going to, so it's going to accelerate under the influence of gravity. As we'll see, it's actually going to slow down in response to surface tension. So you can think about that now, and it should come out in the, they'll come out in the analysis. Basically, as the thing gets thinner and thinner, the pressure inside gets higher and higher. So there's going to be a pressure gradient along the length of the jet, which is going to slow it down. Just do a slightly better job of drawing. Okay, so let's assume that we don't have to worry about viscous effects. So if the Reynolds number is sufficiently high, we can just say we have a uniform flow profile, and we have.
So John.
Yep.
So the increase of the pressure, when it's thinner, it slows down. That's just basically a Bernoulli effect. From Bernoulli.
Sorry, what was that again? It's basically an accelerator. Yep.
The pressure goes down, goes up because it's becoming thinner.
Yeah, that's right. That's because of the curvature pressure, right?
Curvature pressure.
Yeah.
And so it slows down because as pressure goes up, velocity goes down due to Bernoulli law.
That's right. Yeah. So we're basically, we know that gravity wants to accelerate things, but as it gets thinner, the pressure inside gets higher, and so you have an adverse pressure gradient, which is going to resist the falling. Okay? So if we look at 2 points, A and B, so right here and right here. Okay, so that's the initial, that's the inlet speed U naught. Okay. And we can relate PA and PB, so at any 2 points, let's just call this P here to be clear. This is arrow of Z, this is B. So the curvature we can express, as the divergence of the normal in general. And if we can identify the two principal radii of curvature, then we can express it in this way so that one curvature is this curvature and one curvature is that curvature. So let's try and draw that. This is R1, so at this point here, and R2 is something huge. Okay, so there's that radius of curvature, and there's that radius of curvature. Okay? And one is clearly much bigger than the other. So we can just say that. So we can get the curvature pressures at points A and B. Okay, so this is the jump in pressure as we move across the interface. Okay, so we can sub in here. Okay, and so this then gives you the velocity as a function of height. Okay, and then you see Z, A. Okay, so this is saying that the so this is speeding up due to gravity, and this is slowing down due to the surface tension. So again, as the thing gets narrower and narrower, the pressure inside the jet gets higher, owing to the surface tension. Okay, and so these numbers here, Froude number, so this is inertia, gravity. This is so-called Froude number. And then we have our old friend, the Weber number. Okay, one of my, this Froude number, the way I always remember this one, comes up a lot in biomechanics problems. So if you imagine that a creature is an inverted pendulum with leg length A, then and it's moving at a characteristic speed u, then that's the ratio of, so this is again, consider this a pendulum, then that's the ratio of the inertial force which wants to cause it to take off, right, when it's at the apex of its orbit. So when you're running like this in the top of your orbit, there's a lift force. Let's consider it. So at this point here, there's your centripetal force wants to lift you off, and gravity wants to pull you down, right? So the ratio of those two forces, centripetal, so mu squared over a, and then you have gravity mg. So the ratio of those two forces is the Froude number, right? And so it turns out that the gait changes in horses, for example, when they go from walking to trotting to cantering to galloping, happens at discrete values of the Froude number, right? Because it's basically, again, it's this ratio of the centripetal force upwards and the gravitational force downwards. Okay, so okay, now we know in the system so Q is independent of height, so this is going to be 2 pi r Okay, so this will also give you the radius. So you can just substitute in there. Okay, notice this has R in it. So we have to invert, but we can solve that. And let's just look in the high Weber number limit, where inertia, where this surface tension isn't particularly important. So in this limit, you get what you'd expect intuitively, which is the thing getting faster and thinner in response to gravity. But we know that this is resisted by surface tension. Moreover, we know from common experience that the system is unstable, right? So you're actually not going to get an infinitely long jet. The thing is eventually going to pinch off, and that's the problem we're going to look at next. This is a really classical problem in interfacial fluid dynamics called the Rayleigh plateau instability. And this is there's a bit of algebra in this one. So I actually have a handout I should give you guys. Did I leave the handout in my office? I did. I'll get it at... Really? Yeah, okay. I'll get it at the interval. But I have most of the stuff I have. But so the basic mechanism is it's important to understand this. So if you have basically you have a volume of a cylinder of fluid, and it's going to pinch off into droplets. So this is something we know, again, every time you turn on your tap. And so energetically, then has to be the case that this series of drops that you get has less surface area than the original one, right? Surface tension isn't changing, it's just the surface area, and the surface energy is the product of those two. So in the case of the system is acting to minimize surface area. Okay? But so we know that that's our guiding light in all of these interfacial problems. But how do we understand it mechanically? Okay, so if we have this cylinder and we put let's just imagine we put an infinitesimal perturbation on it, right? So we basically put on this undulation. If we do that, we know that we have a neck here. So in this neck, the surface tension is going to be relatively high, right? Relative to here, right? Because the dominant curvature is this one, right? So as we saw there, we can express the curvature as the sum of the two principal radii of curvature. One is this and one is this. And this one's much larger, so the dominant curvature is this. So we can basically convince ourselves that the pressure is going to be high in the neck region relative to the bulbous region, right? Just because this radius is less than this one, okay? So again, you always have atmospheric pressure here, and so then you have a jump which is proportional to surface tension times the divergence of the normal, and the pressure will be higher in here, right? So the pressure is always higher inside the tube than outside, and because the radius of the tube is smaller here, the curvature pressure, Laplace pressure is higher in the constriction in the bulbous region. That being the case, if you put this perturbation on, it's going to grow, right? Because the pressure is going to be high there, so it's going to force fluid out, right? So that being the case, you put this perturbation on, it's going to grow. So that's the basic mechanism for it, okay? So that's a linear argument, which is valid if you have a sort of long wavelength disturbance. And we're going to see that this only works if the wavelength is sufficiently long. Okay? So have you guys done some linear stability analysis? A little bit?
Linearizing the system, looking at eigenvalues a little bit.
Yeah. Okay.
In a more abstract
So,
sense, I think.
okay, because I have notes on this which I'll give you, but the basic principle is to say, okay, here's a steady state, and you do this a lot in fluid dynamics. You say,
You'll see that in the course.
Yeah. Okay. You say basically, here's a steady state, and now we're going to perturb it, and we're going to see whether the perturbation grows. Okay, and it becomes tractable because we know Navier-Stokes are very ugly equations, but you linearize. You say, well, this perturbation is infinitesimally small, right? So when you have nonlinear terms, you're multiplying very small things times other very small things, so they disappear. So basically, you just linearize the system equation. So you just have you have a linear system which you can then solve, and then look to see which perturbations grow. Okay. And so you basically look for here, for example, we're going to look at waves. So basically, something characterized by a single wavelength, and so it's going to have a form which is like e to the I omega t. And so we're going to look to see whether this, if omega is complex, then you have the possibility of its growing exponentially. Right? So we're looking for modes that grow exponentially in response to perturbation. We'll do this a few times. We'll also do the classic wind over water, which I've mentioned. So there again, you have a basic state, which is a flat interface, and then you perturb it, and you look to see which wavelengths grow. And what you typically find is that some mode will have the fastest growth rate, right? And so if you imagine that in a physical system, there are always perturbations around. So there's if you have an infinitesimal thread, there will be wind, there will be this, and any disturbance can be decomposed into basically modes of disturbance, and then so you basically imagine that a fluid system is always being excited randomly, and if it has so if it's unstable to some component of the disturbing force, then it will explode, right? So you basically look for the most unstable mode, and that's the one that you're going to see. So that's the one with the fastest growth rate. Okay, so let's let's develop this from the beginning. So this is. So this is. Okay, so we're starting with the fluid column. A cylinder. Quiescent just means not moving. We're going to assume it's also inviscid, so we're not going to worry about viscosity. We want to see if and when this thing goes spontaneously unstable. Okay? So let's give the unperturbed radius, call the unperturbed radius R0. Okay, and whenever you do linear perturbation analysis, the first thing you have to do is look at the steady state. So here our steady state is that the velocity field everywhere is 0, and the pressure field is going to be P0 plus sigma over R0. Okay? The two radii of curvature, the one is infinite, and this is the other. And let's just, for the sake of argument, say this is 0. P0 is 0. Okay, so we basically just have a pressure inside. Okay, so we're going to perturb it. So we're going to say the new radius is going to be R0 plus this small perturbation, e to the omega t plus I k z. Okay? So these are undulations along the length of the tube. Okay, and so we've made the argument already. If we put on such a perturbation, we're going to have high pressure here relative to here. And so we expect the instability to grow, but we want to know when it's going to grow. How does that depend on the wavelength? So K here, so the wavelength of disturbance, lambda equals 2 pi over K. Certain wavelengths are going to grow faster than others. So basically we're going to ask how does omega, in order to assess the fastest growing mode, we have to see how omega depends on K. And that's called the dispersion relation, so that's what we want to deduce. Right? Once you've got the dispersion relation, we say, the fastest growing mode. You can see that's where we're going. That's what we're going to derive. But we need to see how omega depends on K.
And this is a comment, this is like numerical methods of Fourier analysis, right? For a method where this is very visible.
Okay, and so this is linear analysis, so we're assuming that this is very small relative to this. So that's by assumption. Okay, so we need to know how the perturbation velocity evolves as a function of time. Okay, so those are the two components, radial and longitudinal. And our perturbation pressure we'll call P twiddle. Okay, and so we have to look to see how these evolve. Now these evolve according to Navier-Stokes. And we're assuming that this is inviscid, so we don't have to worry about viscosity. Okay, and when I say linearizing, these things are all of order epsilon. Okay, so this is order epsilon, this is order epsilon, this is order epsilon, this is order epsilon. So if we have, for example, the nonlinear terms in Navier-Stokes, u dot grad u, those terms go. So those become order epsilon squared. So when I say linearizing, I mean retaining terms which are only linear in epsilon, that is to say, epsilon squared terms we get rid of. So you need to look at the radial, so the radial and so the R and Z components of Navier-Stokes. So we know in general this will also have a u dot, a nonlinear term, but we can throw that out because we're linearizing. And then there's the viscous term, which we can throw out because we're neglecting viscosity. And then the Z component and then we have, so those are those are the momentum, two components of the momentum equations. And we also have continuity. So that's div u is equal to 0, which in cylindrical coordinates takes this form. Okay, and so we anticipate, we're basically looking for these wave-like solutions, so we expect this form for dependence on z to be the same for for the velocities and pressures. Okay. So we expect wave-like solutions. We expect dependence of all of these field variables on z in time to be the same. We can have some radial dependence, so we really just need to find the form of these three functions of R. So we're going to sub these in here. Okay, so these come from these two equations, from momentum equations, and now the continuity equation gives us okay, so what we do is we sub this, solve for z from here, sub it in here, then we take a derivative, and we get a single ODE for R. Again, I have some, I have notes. So if we eliminate z and p, we have three equations, three unknowns, so we can get one equation for the one unknown, that being R, which is again, R is the radial eigenfunction on the velocity, on the radial velocity. And happily, we get an equation which we all recognize. Okay, so that's our equation for the R dependence of the velocity. And once we've got that, we can use these other relations. So once we've got R, we can calculate P from R and Z from P. Okay. Okay, so this is a modified Bessel equation Look familiar? So, okay, so solutions. These are modified Bessel functions, the first and second kind. Okay. Okay, so these K's, K1s blow up as R goes to 0. So these are the only survivor. So our solution, our desired solution, C I1 of K. Oops, I1 of KR. Okay, where C is an unknown constant. Okay, so that's the form of the solution. We have to still find the coefficients, and ultimately we're going to get to this to tell us how the different disturbances grow as a function of their wavelength, which is of course related to k. And we want to find the fastest growing. Now, this is the ultimate goal here, is omega as a function of k. Okay, so pressure. So we're going to use these equations here, which relate pressure to R and Z to pressure. And we can use the Bessel function identity. So Bessel functions, it's just the standard eigen. Whenever you get a del squared operator in a problem, so in a diffusion problem in cylindrical coordinates, you always get Bessel functions, so they're just the sort of basis for the cylindrical coordinates, just like sines and cosines are basis in Cartesian. So this gives us pressure. Now we're going to apply the boundary conditions. So the kinematic So that's just saying that the rate of change of the radius is equal to the local radial velocity. And that gives us C. Okay, we haven't applied the normal stress balance yet. Again, one has to use everything to solve the problem. In Navier-Stokes, one has to use the boundary conditions. Ultimately, we'll get to the dispersion relation. Okay, so we know the normal stress boundary condition looks like. So again, we're going to use this approximation if the thing is long and thin. You can express it as these two radii of curvature, one of which is simply the local radius of the cylinder. So let's so at this point here, so we can call R1. So R1 is a function of Z, and the other radius of curvature is this guy. Which is much greater. But we're going to calculate it exactly. Okay, so these are the principal radii of curvature. Okay, we know that we've expressed R1 as R naught times 1 plus epsilon over R naught. So this is our exponential. Let's just leave it as x for the moment, but we see that it takes this form. So correct to linear order. Okay, this is this exponential here. Okay. And then we have 1 over R2. So this we can actually calculate using we've already calculated the curvature, so just from a single, basically the curvature of a line. Right, so this radius of curvature we can calculate simply by treating this as an arc in the plane. Okay, so that's the second radius of curvature. So we get, so we can express this one as 1 over R naught. So again, correct to linear order, minus epsilon over r naught squared e to the omega t plus I to the z. And this one okay, so we can, if we substitute in here now, we get okay, and this cancels because that's the zeroth order balance. So now we have the waveform for the pressure disturbance. And we're almost there. Too much algebra. But the concept is very important in hydrodynamics, the idea of linear stability analysis. Okay, so oops. Okay, so we know this is by definition E of R e to the omega t plus I a z. And we solved this already. This is going to give us C. Oh, we have C already, sorry. Or not. Okay, so this is actually going to give us the dispersion relation. That is to say, we now have a relation between the growth rate and the wave number. Okay, let's take a break and we'll talk about the physics after the break. You need to go. Too much algebra.